So in our last lecture of circular motion, we studied about v, that is the linear velocity, and its relation to the newly defined angular velocity omega. In this lecture, however, we'll try to understand why v is written as omega cross r. So we'll try to understand the origin of this cross product. Agreed? So see, whenever you have something written in terms of cross, it means these things are generalized. Okay, for example, consider um, an object moving in circular. Consider a rod. Okay, and consider this is the origin. So in place of taking the origin exactly at the center of the circle, now what I've done is, let me take the origin somewhere around here. So this is the origin O. Now imagine that there is a rod, okay, of a particular length, and that rod is here. Agreed? And the tip of this rod is undergoing a circular motion. So it is moving like this. So the tip of the rod is undergoing a circular motion. And let the velocity, the linear velocity of the tip be v. I mean, the tip of the rod is moving along the circle. Okay, the tip of the rod is moving and tracing a circle, and the tip of the rod is moving around the circle with a tangential velocity v. Agreed? Now, we all know that if there is a velocity tangential to this circle, so this velocity is v, then we can define a velocity omega, which is called as the angular velocity, and omega is related to v with respect to the radius. So let r be the length of the rod. Okay, then can you tell me what will be the radius of this circle? See, the black circle is the circle that the rod is tracing out, that the tip of the rod is tracing out as the rod is moving round and round and round, and the one part of the rod is fixed at this point O. Agreed? So what is this distance from center to this part? So this distance will be, so consider if this is theta, then of course that distance will be r sine theta. Agreed? So this is also a case of circular motion where you have taken a rod, one part of the rod is fixed to a point, and another, the tip of the rod is moving in a circle, and you see that the distance between the circle traced, that is the center of the circle traced, and the edge of the circle is r sine theta. So if I want to now relate these three quantities, this is the v, the r sine theta, and the omega, then what will be the relation? Of course, the relation will be velocity equals to omega into the radius. Now what is the radius now? The radius now is actually r sine theta. Agreed? Where r is the length of the rod. So anyhow, this is a general case where you have a sine theta. So whenever you have a sine theta, what do? You write v is equals to omega cross r. So the reason we write v is equals to omega cross r, the reason we write the cross product is because it takes into consideration all the special cases. One special case of this is when sine theta is 1. So when sine theta equals to 1. So when sine theta is 1, when the theta is exactly 90 degree. So what do you mean by theta 90 degree? It means the angle between omega and the radius is 90 degree. Here you see the angle between omega and the r is theta. The angle between the omega and r is theta. However, when you look at this 2D circular motion, so this is a complete 2D circular motion, then the angle omega comes out of the screen. The direction of omega is outward to the screen, and you see that omega, and this is my r. You see that omega and r, the angle between omega and r in this case is 90 degree. I mean omega is perpendicular to r. Okay, look at this case too. This omega, there is a omega here, and look at the black line that I'm going to draw. This is my r. So you see omega in this case is perpendicular to r. But this is one special case where omega is not perpendicular to r, but omega and r, okay, the angle between omega and r is theta. So whenever you see a cross product, just remember that the entire thing has been generalized. So when theta is 90 degree, then what we have v is equals to omega r. So remember, v is equals to omega r means that the theta is 90 degree, and this also means that we are considering a direct 2D motion where the radius and the omega are exactly at 90 degree to each other. Agreed? Now what we'll do is, now we'll talk little bit about acceleration. You know there is a acceleration. It's natural. Wherever there is a velocity, there has to be an acceleration. Okay. So let us study a bit about acceleration now. So an interesting thing happened. That interesting thing is, if so initially we considered an object moving at a velocity of 5 meter per second. If you look at the lecture number 1, this was 5 meter per second, and the object seems to be moving at a constant velocity along this circle. Now imagine that instead of moving at this constant velocity, the object moves at an acceleration a. I mean, the velocity of the object is always changing with respect to time as it is moving along the circle. Okay, what type of motion is this? This is this accelerated motion. For example, here the object say has 5 meter per second velocity. Okay, just after 1 second the velocity is 10 meter per second. Okay, just after another 1 second the velocity is say 15 meter per second. Okay, this is an accelerated motion where the velocity of the object is changing, I mean increasing all along the circle as it is moving. So what is the acceleration? Can you guess the acceleration now? Obviously the acceleration is 5 meter per second square. It means in every 1 second the velocity is increasing by 5 meter per second. Agreed? So what you can see here is, if there is a change in velocity, I mean if there is a change in velocity, of course there will be a change in the angular velocity. Agreed? But there won't be any change in radius, that is for sure. Okay, now what we need to do is, you just divide time in both sides. So write a del t here and a del t here. So what is dv by dt? dv by dt directly corresponds to a tangential acceleration. Agreed? And if this is so, if a particle is moving along the radius with a particular tangential acceleration, then of course the angle covered with respect to time is also accelerating. I mean, initially we had omega as what? We had this omega as pi by 2 radian per second. What is the meaning of pi by 2 radian per second? It means in every 1 second the object was covering an angle of pi by 2. But now this is not the case. Since the velocity is also changing with time, our omega will also change with time. So if the velocity changes with time, this leads to an acceleration. You have learned about this acceleration already in the one-dimensional motion, and the rate of change of angle with respect to time, so rate of change of angular velocity with respect to time is called as the angular acceleration, that is denoted as alpha, and this is written as alpha cross r. So what is alpha? Alpha is your angular acceleration. See, omega is what? Omega was your angular velocity, and alpha is an angular acceleration. So if an object has angular acceleration, it also means that the tangential velocity is also changing with time, because they are both related to each other. Agreed? So why are we defining this type of things? It will make our study of circular motion easier. That's why we are defining all those terms. So we'll continue more on our discussion of circular motion next class. So what did we learn till now? We understood there is a velocity. We understood there is an angular velocity. With the tangential velocity, there is an acceleration a related to it, which is equals to rate of change of tangential velocity with time. With omega, there is an acceleration alpha related to it, which is rate of change of angular velocity with respect to time. But there is something amazing and interesting about circular motion that we actually do not have in the one dimensional motion, and that amazing thing we'll do in our next lecture.